Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will talk about the gamma function. And we are going to be talking about it because this is an important ingredient to define the PDF, probability density function, of a random variable with a gamma distribution. We will talk about that later in another video. Okay, let's begin. First, let's define the gamma function. That's what we're going to be doing first. I'm going to give you the definition of the gamma function. Then I will show you a couple of examples, and at the end of this video what we're going to be doing is showing an important property of the gamma function. Okay, so first, definition. Okay, so the gamma function is defined by an integral. Okay, so the gamma function is defined by, as I said, it's defined by an integral, and this is the letter, the uppercase gamma, right? So gamma, it's a function, and it has as argument, as a parameter, alpha. Okay, so gamma evaluated at alpha is defined to be the integral from 0 to infinity of y to the power alpha minus 1 times e to the negative y dy. Okay, and that will be for positive alphas. Okay, looks better. Okay, oh, there we are. So that's how the gamma function is defined. Let me give you an example. I know that the first time I saw it, it was kind of scary, right? It looks kind of imposing. It's an imposing expression, but let me show you that you have seen something like that before. So example number 1. So we know that this expression holds for any positive alpha. Okay, so let's see what happens if we evaluate the gamma function at 1. Okay, see what happens. So wherever we see an alpha, we will have a 1. We're going to be substituting by a1. Let me copy paste that. Going to get rid of the last part, this here. Okay, so now we have a 1 instead, right? So that happens to be just, guess what, y to the 0 power. That's just a beautiful 1. So in the end we have the integral from 0 to infinity of e to the negative y dy. Okay, so let me copy paste this. I don't need that there. Okay, I don't need that. So it's just the integral from 0 to infinity of e to the negative y dy. But take a look at that integral here. Remember that we have already talked about another probability distribution called the exponential distribution. Remember that the PDF for an exponential distribution with parameter beta is given by 1 over beta e to the negative y divided by beta. So this guy, e to the negative y, happens to be an exponential with parameter beta equal to 1. And we know that the non-zero part of an exponential goes from 0 to infinity, right? That's the region where a random variable with an exponential distribution is non-zero, right? And we know that exponential distributions are legit random variables, legit PDFs. So when we integrate from 0 to infinity an exponential, that's just 1, right? Okay, so as you can see, gamma at 1 is just 1, or in other words, it's just remember that we showed that exponential, random variables with an exponential distribution are legit PDFs, and one of the properties that you have to show is that the integral from negative infinity to infinity of the PDF is 1. So we have done something like this before anyway. So gamma evaluated at 1 is just 1. Okay. Another example. Oh, come on. That's better. Example number 2. Let's see what happens if we evaluate the gamma function at 2. Okay? So gamma at 2 will be something similar to this, but now instead of a 1 here, we are going to have a 2, right? Okay, so let me copy paste. It might be useful. And then we're going to be making the necessary changes. So this turns into y, the integral from 0 to infinity of y to the power 2 minus 1 times e to the negative y dy. That's just by the very definition of the gamma function. Okay, so now the next integral is going to be just this is just y, right? You guys agree? But then you go, if this is the PDF of an exponential with parameter beta equal to 1, then y times that PDF, it's just the expected value of an exponential with parameter beta equal to 1. But remember that in another video we showed that in general, if you have an exponential with parameter beta, the expected value of that exponential will be exactly beta, right? So in this case, this integral is just 1, right? Because beta, the beta in this case, happens to be 1. So another value of the gamma function. Gamma evaluated at 1 is 1. Gamma evaluated at 2, 1 as well. Okay? Okay, nice. So at this point I have given you the definition of the gamma function. We have talked about a couple of examples. So we have realized that we have dealt with something like this before. It's not as bad as we thought. And as you can see, when you evaluate the gamma function, you end up with a constant. And that's exactly why we needed to talk about this gamma function. This gamma function is going to help us come up with the right constant, the constant that is going to allow us to talk about another important family of probability distributions, the gamma distribution. And this guy here, the gamma function, is part of the definition of the probability density function for a random variable with a gamma distribution. Okay, it's going to make sense later. But bottom line, what I want you to see here is that when you evaluate this gamma function, you end up with a constant. Okay, so not such a terrible thing. So the next thing, the last thing that we were going to be doing in this video together was talking about an important property of the gamma function. Okay, so it turns out that the gamma function has this property. There's kind of there's an interesting relationship here. So it turns out that gamma evaluated at alpha, let me copy paste this guy here, the gamma function evaluated at alpha equals alpha minus 1 times the gamma function evaluated at gamma, the gamma function evaluated at alpha minus 1. Okay? And guess what? We already have an example for that. Example. If alpha is 2, then if that property is true, then we should have 2 minus 1 times gamma at 2 minus 1. But that happens to be just, 1 times gamma at 1, right? Meaning this gamma at 2 must be equal to gamma at 1. That holds, right? Well, that holds in general for this property that I'm showing you here, holds for any alpha greater than 1. Okay? And this is just an example, right? What we had here. So it holds. Okay. Let's try to show that property in general. Proof of that property. So we are going to start with the definition of the gamma function. Okay? So by definition, the gamma function is this guy. Right? Let me just copy. I don't need this guy here. Just this part. Okay. I'm going to try and get rid of the last part. Okay. So that's just by definition. Okay? No problem. But now I want you to recall something that you and I did together in another video. Remember when we talked about the exponential distribution? Remember when we talked about the expected value of an exponential distribution? We had a similar we had to find a similar integral, right? But in that case we just had y times e to the negative y dy, right? So what we did there, right, was we integrated by parts. So here let's try and do that and see if that works to show this. See if we can come up with that relationship. Okay? So integrating by parts, so just like before, but now we have instead of y to the alpha minus 1. So let u be y to the power alpha minus 1. Okay. And then du, right, clearly is going to be alpha minus 1 times y to the alpha minus 2, right? Let me copy paste that guy first, then I'm going to change it here in the exponent and dy, right? No mistakes? Okay. And then dv necessarily is going to be this guy, e to the negative y dy. And integrating that guy is not that hard, right? It's going to be just almost itself, just we need a negative sign here, right? So when we take the derivative of minus e to the negative y, applying the chain rule, what we have is that constant minus 1 e to the negative y, right, times the derivative of negative y, that's minus 1, and then you end up with this, right? Good. Okay. So now let's plug in, right? We know that this integral is going to be the same as u times v, right? So it would be this guy times this guy, but it's times, so let me place that negative sign here in front, right? And we're going to be evaluating this expression here, right? We're going to evaluate, oops, not what I wanted to do, but let me just copy paste it here. This is what I want. I want it here. I want to evaluate it here, 0 and infinity, right? Okay, that's better. So we have u times v, right? And then we have minus v du, right? So we have v du, right? So let me write it down here, and it's going to be the integral from 0 to infinity of v du. So it's going to be this guy here times this guy here, and then we're going to rearrange it. Okay, so let me place that alpha minus 1 in front. This is going to be a minus times a minus. Let me turn that into a plus, right? And now just so we see the resemblance more easily, let me place that y to the alpha minus 1 to the alpha minus 2 here, right? But this is just that product, right? v du. That's what we have here, okay? Now, I want you to take a closer look at the first term, right? So we have that product, y to the power alpha minus 1 e to the negative y, evaluated at infinity and 0. Okay, so e to the negative y. When y goes to infinity, we know that this guy goes to 0, right? However, this guy minus y to the power alpha minus 1 is going to negative infinity, right? But it can be shown that this exponential here goes faster to 0 than y to the alpha minus 1, okay? Is going to negative infinity. And remember that also when we talked about the expected value of an exponential, I provided a numerical argument that this is true. So anyway, the point is that when you evaluate that product, when y is increasing without bound, then that is going to be 0. And when you evaluate that product at 0, it will clearly be 0, right? So don't worry about the first term. Now what we have is this guy. So let me copy paste that guy. That's the only one that matters. Now let me factor out that alpha minus 1. That's a constant, right? So I get to pull it out by the linearity of integrals. But now take a look at this guy. It's the integral from 0 to infinity of y to the power alpha minus 2 times e to the negative y. If you take a look at the definition, the gamma function evaluated at alpha is the integral from 0 to infinity of y to the alpha minus 1 power e to the negative y dy. Well, then this guy here must be gamma evaluated at alpha minus 1, because that alpha minus 2 could be rewritten like this. Alpha minus 1, right? You agree? So what we have here is, in the end, what we have is that gamma at alpha happens to be just alpha minus 1 times the gamma function evaluated at alpha minus 1, right? So we have shown the property that we wanted. Okay? So, in summary, what we did here in this video, you and I together, was first, we introduced the gamma function. We talked about a couple of examples of the gamma function. What we saw is that when you evaluate the gamma function at some number, you end up with another constant. Okay? So, then we showed that there's an interesting property of the gamma function, that gamma evaluated at alpha for an alpha that is greater than 1 is just alpha minus 1 times gamma to the alpha minus 1. Something interesting also, and let me just mention that, is this. Note, if you have an integer, right, if n is an integer, then gamma evaluated at n is n minus 1 factorial. Okay? Okay, but again, this is provided that n is an integer. For instance, gamma at 2 is going to be 1 factorial, and 1 factorial is 1. Right? Oh, yeah, okay. So, anyway, that's it for now. We're going to talk a little bit more about this function where we will use it to define the constant that is going to make the expression for the PDF of random variable with a gamma distribution to be a legit PDF. Okay? So, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.